When we saw protocols implementing reliability like go back N and selective repeat, we had to understand when the protocol expects the packets not to arrive. Somehow it had to do with the RTT value because it couldn't be any smaller than that. Why? Because this is exactly the time it takes to travel between sender and receiver and back. The RTT also changes over time. But how big is it? For protocols implementing reliability, like in the case of go back N, we have the timer for the old packet in the ear in selective repeat protocol. We did this for every packet that was in the air. But in any case, if we chose a smaller timeout size, we might have thought there was a packet drop even before it arrived. If we select a bigger timeout value than we need, the reaction time of the protocol to packet drops will be slower. As we said, this has something to do with RTT. The RTT is also a variable. So how do we estimate RTT? We can measure the RTT for the first time and call it sample RTT. As we sample, measure, the time. We will measure it for each segment, save the time it takes to send the segment, and get back to the ACK. Of course, retransmission time does not count up and doesn't influence the average. The problem with this method is that sample RTT can change rapidly because of the network infrastructure. To get something finer and easier to use, we will count the average value over a certain period and call it RTT, which will be used in our protocol. Now we'll see how we really calculate it. Let's look at how we calculate the estimated RTT, given the estimated RTT we have on hand right now and the sample RTT we just found. We'll weight these two values with some weighted A, chosen empirically, and its length is 125 milliseconds. You can see that the estimated RTT is 1 minus A times estimated RTT plus A times sample RTT. What does it give us? It lets us ensure that the effect of the sample RTT which happened in the past decreases exponentially. That is what it means. So we will converge on the value of the estimated RTT more gently. So now let's look at what the RTT deviation can be, and then we'll use that value to calculate the timeout. So first of all, what did we say? We said that a bigger estimated RTT, so the safety margin we need to take inside the timeout has to be even bigger. So because of that, let's try to think. How can we assess the deviation of sample RTT from the estimated RTT? We'll call this value dev RTT or deviation RTT. Inside, we'll also weigh in the dev RTT we have on hand, and the sample RTT minus estimated RTT, the difference between them. So, we'll take the difference in weighted beta, which we chose empirically, like 25 milliseconds, and we'll take dev RTT with weighted 1 minus beta. So we have the dev RTT in hand so that this is exactly the safety margin we'll take. Empirically, this is 4 times dev RTT. We'll sum it together with the estimated RTT. This will be the value of timeout. The estimated RTT changes more, so the safety margin should also be bigger. This is how we'll try to assess the size of the timeout, which will give us the option to indirectly understand that the packet didn't arrive.